How is efficiency calculated for thermodynamic cycles? Have you ever wondered how machines convert heat into useful work? Understanding this process can be fascinating. Let's break down how efficiency is calculated for thermodynamic cycles. Efficiency, often referred to as thermal efficiency, measures how effectively a cycle transforms heat energy into work. To find this efficiency, we look at the ratio of the net work output to the heat energy input. In simple terms, it tells us how much of the heat energy supplied is turned into work instead of being wasted. The formula for thermal efficiency is straightforward. It is expressed as the work output of the cycle divided by the heat input to the cycle. This can also be written using heat terms directly. The equation shows that efficiency equals the difference between heat absorbed and heat rejected, divided by the heat absorbed. In this context, heat absorbed is the energy taken in from a hot source, while heat rejected is the energy lost to a cooler source. Since some heat is always lost in any process, thermal efficiency will always be less than 1 or 100%. The efficiency of a thermodynamic cycle is influenced by the temperatures between which the cycle operates. The theoretical maximum efficiency for any heat engine working between two heat sources is defined by the Carnot efficiency. This maximum efficiency is calculated using the absolute temperatures of the hot and cold reservoirs. For specific cycles, such as the Otto cycle used in gasoline engines or the diesel cycle, efficiency can relate to factors like the compression ratio and specific heat capacities. For instance, in the Otto cycle, the efficiency depends on the compression ratio and the specific heat ratio. Increasing the compression ratio can improve efficiency, but there are practical limits due to engine knocking. In real-world applications, engines typically achieve efficiencies lower than ideal values because of friction, heat losses, and other factors. Generally, real-world efficiencies range from about 25% to 50% of the ideal maximum. Understanding how to calculate efficiency is essential for designing better engines and power plants. By focusing on maximizing work output while minimizing heat loss, we can improve energy conversion. Higher operating temperatures and improved cycle designs lead to more efficient energy use. So, next time you think about how machines work, remember the fascinating calculations behind their efficiency.